Hello everyone, my name is Qi, and I'm a postdoc researcher at the University of Oxford. I'm here to present our paper comparing labeled Markov decision processes. This is joint work with Professor Stefan Kiefer at Oxford. Let's start by introducing the model of interest, labeled Markov chain, an LMC, which consists of a finite set of states, a probability transition function which maps each state to a probability distribution, a set of labels, and each state is labeled with an observable letter. Let's use this big M to specify the transition matrix, so that given a label A, two states S and T, the entry is equal to tau of ST, the transition probability from S to T if S is labeled with A, and 0 otherwise. The sum of M of A over all labels is a stochastic matrix, and also this big M can be naturally extended to a finite trace. This slide shows an example LMC where the colors represent the labels of the states. So SA and SB have different colors, so they have different labels, A and B respectively. Each LMC generates an infinite sequence of labels randomly. Let W to be a finite trace, and let the event to be the set of all infinite traces with prefix W. Then an LMC with initial distribution mu assigns to this event a probability the product of mu m of W and 1 vector. This 1 vector is a column vector where all entries are ones. So in this example, if the initial distributions are deltas S, delta T, the direct distribution on S and T, the probabilities assigned to the infinite traces with prefix AAA or the infinite traces with prefix AAB would be a half. And in fact, for this LMC, the probabilities are always the same for delta S and delta T. W can be any finite traces. We consider two natural notions of equivalence for LMCs. One is choice equivalence. Two probability distributions are choice equivalent if and only if, for all finite traces W, the probabilities assigned to the event, all infinite sequences of labels with prefix W are the same for mu and nu. The other notion is probabilistic bisimulation relation. It is an equivalence relation, and two states are related if and only if they have the same labels, and the probabilities to the same probabilistic bisimulation class E are the same for S and T. And the probabilistic bisimilarity is the largest probabilistic bisimulation. Let's go back to the previous LMC example. As we have already mentioned, the probabilities are the same for delta S and delta T, where W can be any finite trace. And this implies that delta S and delta T are trace equivalent by the definition of trace equivalence. However, S and T are not probabilistic bisimilar. This is because S prime and T1 are not probabilistic bisimilar. They transition to the probabilistic bisimulation class, which contains SB with different probabilities. From S prime, it is a half. From T1, it is 0. And since S prime and T1 are not probabilistic bisimilar, S and T are not probabilistic bisimilar. Then two distances are induced by these two notions of equivalence. The one induced by trace equivalence is total variation distance. It is on a pair of probability distributions, denoted by dTV, and it is the maximal difference of probabilities that assigns to the same measurable event. And in fact, this soup can be replaced by max. This is proved by Chen and Kiefer in their Leaks paper that a maximizing event always exists. Total variation distance 0 is equivalent to trace equivalence. Furthermore, the total variation distance 0 can be decided in polynomial time, and there's a polynomial time algorithm to decide total variation distance 1. The distance function induced by probabilistic bisimilarity is called probabilistic bisimilarity distance, denoted by dPb, and it is on a pair of states. It can be defined as a least fixed point of a function. In parallel with the total variation distance, the probabilistic bisimilarity distance 0 is equivalent to probabilistic bisimilarity, and it is also polynomial time to decide probabilistic bisimilarity distance 0 and 1. Having introduced the labeled Markov chains, now let's move on to the other model of interest labeled MDP. It is very similar to LMC, but this model has non-determinism. In addition to LMCs, MDP has a set of actions, and instead of the probability transition function tau, it has a partial function phi which maps state and action pair to a probability distribution. We will see an example soon. A memoryless strategy for an MDP is a function alpha from S to a distribution over the actions. And a strategy is called MD, memoryless deterministic, if we only allow a state to choose one action. And we can view MD strategy as a function from a state to an action. So given a memoryless strategy alpha and a labeled MDPD, an LMC D of alpha is induced. And let's use this big M with subscript alpha to specify the probability transition matrix in the induced LMC. This slide shows an example MDP where all the states have only one action except state Q2. It has two actions, M1 and M2. And for this MDP, S and T are probabilistic bisimilar if and only if Q1 and Q2 are probabilistic bisimilar, or Q2 and Q3 are probabilistic bisimilar. So if we are only allowed to use MD strategies in this MDP, for example, we let Q2 to choose M1, then Q1 and Q2 only has transitions to U. This makes Q1, Q2 probabilistic bisimilar, which in turn makes S and T probabilistic bisimilar. So S and T will always be probabilistic bisimilar in the LMCs if we are only allowed to use MD strategies in this MDP. As we have mentioned, that it is polynomial time to decide total variation distance 0 and 1, so we might ask ourselves similar questions on MDPs. Let's first have a look at this trace inequivalence problem. So given a labeled MDP and two initial distributions mu and nu, the trace inequivalence problem, or TV greater than 0, asks whether there's a memoryless strategy alpha such that mu and nu are trace inequivalent in the induced LMC. Let's recall the definition of trace equivalence. So the probabilities assigned to the infinite sequences with prefix W would be the same for mu and nu. Let's define a vector space in which all vectors are of the form M alpha of W times 1. Alpha can be an arbitrary memoryless strategy, and W can be an arbitrary finite trace. Then we can rewrite the definition of trace equivalence to be mu V is equal to nu V for all column vectors from V2. Equivalently, mu and nu are not trace equivalent if there exists a vector V from V2, which makes mu V and nu V different. Then by this definition, our problem is reduced to compute a basis for V2. And to compute a basis for V2, we can just go through all the memoryless strategies. But there's a big problem with this idea. as the set of memoryless strategies is uncountable. So let's define some more vector spaces. So V3 here is very similar to V2, but we are only allowed to use MD strategies for the vectors in V3. This makes V3 to be subset equal to V2. And the vector space V1, for every label, we are allowed to choose a different strategy. And this makes V2 to be a subset equal to V1. Now we have a second idea. If we can prove the vector spaces V2 and V3 are the same, then a basis for V3 would be a basis for V2. And as we only allow to choose MD strategies for the vectors in V3, then to compute a basis for V3, we only need to go through all the MD strategies. But there's also a problem with this idea. That is, the set of MD strategies is exponential, which gives rise to an exponential algorithm. So can we do better? So if we can prove all three vector spaces are the same, then a basis for V1 would be a basis for V2. And the good thing about V1 is that a basis for it can be computed in polynomial time. And indeed, in our paper, we have proved that V1 is subset equal V3, then which means that all three vector spaces are the same. Since a basis for V1 can be computed in polynomial time, a basis for V2 can be computed in polynomial time. Then since V2 is equal to V3, this means if there is a memoryless strategy witnessing mu and nu are trace inequivalent, then there's a witnessing MD strategy. And we can decide this problem TV greater than 0 in polynomial time. What is better is that we not only can decide this problem in polynomial time, we also have a polynomial time algorithm to give us the witnessing MD strategy and the witnessing trace. It is also polynomial time to decide probabilistic bisimilarity distance 0 and 1 for LMCs. So we might ask ourselves similar questions on MDPs. So let's move on to the problem, probabilistic bisimulation inequivalence. So given a labeled MDP and two initial states S and T, the probabilistic bisimulation inequivalence problem, or PB greater than 0, asks whether there is a memoryless strategy alpha such that S and T are not probabilistic bisimilar in the induced LMC. Our first idea is that maybe it is very similar to the trace inequivalence problem for MDP. Since for trace inequivalence problem, if there is a witnessing memoryless strategy, there's always a witnessing MD strategy. So we might also think that it is enough to check just MD strategies for PB greater than 0 problem. However, in the labeled MDP presented earlier, we know that if we are only allowed to use MD strategies in this MDP, then ST will always be probabilistic bisimilar. So only memoryless randomized strategies for this MDP will witness S and T are not probabilistic bisimilar. So it is not enough to just check MD strategies. So what we do is we define an equivalence relation and then we run the classic partition refinement algorithm. Let X be a partition of the state space S, and we define an equivalence relation, we call it equiv_X. Algorithm 1 is the classic partition refinement algorithm, where at the beginning all states are in the same partition, and in each iteration we refine the partitions until we reach a fixed point. We have two lemmas here. The first one states that equiv_X is a subset of a probabilistic bisimilarity relation in all induced LMCs. And the second lemma states that there exists a memoryless strategy beta such that the probabilistic bisimilarity in the induced LMC D beta is a subset of equiv_X. These two lemmas tell us that equiv_X is equal to the probabilistic bisimilarity relation in the induced LMC d beta, and it is the finest of such relations. So if we are given two states S and T, and after running the partition refinement algorithm, these two states are no longer in the same equivalence classes, then this means there is a memoryless strategy that will make these two states not probabilistic bisimilar. However, the algorithm does not explicitly give us the witnessing memoryless strategy. So can we construct the witnessing memoryless strategy in polynomial time? And the short answer is yes. And the key ideas is to pre-compute some prime numbers to form the weights of the actions in the memoryless strategy. And I highlight here that to show this algorithm is polynomial time, we use the prime number theorem. So this problem, probabilistic bisimulation inequivalence, is also in P, and we have a polynomial algorithm to construct the witnessing memoryless strategy. I would like to illustrate using an example how to construct a witnessing strategy. Here's an MDP where S has two actions, M1 and M2. So we first run this partition refinement algorithm, which begins with all states in the same partition. Then this partition is split into two by the labels. Then we need to do some computations to see if this set can be further split. Finally, we reach a fixed point where S and T are in two different equivalence classes. This tells us that there is a memoryless strategy that will make S and T not probabilistic bisimilar in the induced LMC. So we start constructing this memoryless strategy. Let W to be the weight put on action M1 and 1 minus W to be the weight put on action M2. In the induced LMC, we want S and T to be not probabilistic bisimilar. So we want the probabilities to the equivalence classes in partition X1 to be different from S and T. And to make these two numbers different, we could add the condition that the denominators of W to be coprime with the denominators of Q. And this indeed will help us rule out some accidental probabilistic bisimulations. This condition itself is not enough. If we assume that denominator of Q is not a multiple of 3, and by the previous condition, we can choose 3 to be the denominator of W. And if Q is 3 over 8, then S and T would be probabilistic bisimilar in the induced LMC. So we need to add another condition, stating that denominator of W should also be coprime with the numerator 3 here, which is a numerator of some probability differences. So if we choose prime numbers satisfying these two conditions to be the denominator of the weight W, we will rule out all the accidental probabilistic bisimulations. Now let's consider the total variation distance 1 problem. Given two probability distributions mu and nu, the total variation distance 1 problem, or TB equal to 1, asks whether there is a memoryless strategy such that mu and nu have total variation distance 1 in the induced LMC. We have proved in the paper that this problem is NP complete, and the hardness proof is by reduction from the set splitting problem, which is one of Gary and Johnson's classical NP-complete problems. Given a finite set S and a collection C of subsets of S, the set splitting problem asks whether there is a partition of S into disjoint sets S1 and S2 such that no set in the collection C is a subset of S1 or S2. Let's have a look at an example how this reduction works. Given an instance of a set splitting, S has 3 elements, E1, E2, and E3, and the collection C has 2 subsets of S. C1 contains E1 and E2, and subset C2 contains E2 and E3. Then we transform this set splitting instance to an MDP. In the MDP, there is a memoryless strategy that witnesses delta S and delta T, the direct distributions on S and T, having total variation distance 1 if and only if the original set splitting instance is a positive instance. So for this example, the highlighted MD strategy induces an LMC, and in this LMC, delta S and delta T have total variation distance 1. This is because if we start with state S, in the induced LMC, the probability of generating infinite sequences of white labels is 1. And if we start from state T, the probability of generating the same event, infinite sequences of white labels, will be 0. This also gives us a witnessing partition for the set splitting problem, S1 and S2. And we can see no subset in the collection C is a subset of S1 or S2. This table summarizes the results in the paper. In total, we have studied 8 problems. We have focused on 2 problems, TV greater than 0 and PB greater than 0 in this talk. These 2 problems are in P. The other 6 problems do not have polynomial complexity, unless P is NP. We have proved that TV equal to 0 and TV less than 1 are extension theory over the reals complete. And the hardness proof is by reduction from the NMF problem, non-negative matrix factorization. TV equal to 1 and PB equal to 1 are proved to be NP hard, and the reduction is from set splitting, which we presented earlier. The problems PB equal to 0 and PB less than 1 are proved to be NP complete, where the reduction is from subset sum problem. We have completeness results for all these problems except TV equal to 1, where a complexity gap remains. Finally, I'd like to mention a few words of a related model, interval Markov chains, IMC, which is very similar to our normal Markov chains, but the transitions are labeled with probability intervals. Selecting a memoryless strategy in an MDP corresponds to selecting a probability from the probability interval in an IMC. We believe that the lower bounds derived in our paper can carry over to the corresponding problems in IMCs, but it is not obvious to us whether the upper bounds hold or not for the corresponding problems in IMCs. This is the end, and thank you for listening.